So I am now on my third of 4 very exciting yet, kind of sad introductions. I've had the privilege of working with Sarah since her freshman year when she took environmental. I like to cause all sorts of trouble in that way. And Sarah's been a joy to work with in lab and out of lab and in these conversations because she's sneaky. She goes off and does these great things, and then she's just like, oh, I did this lovely internship. Oh, I did this lovely REU. And so as some of the most, I will always appreciate Sarah because she will surprise me with what she has done and what she is engaged in. And every time I ever ask her to do something, she took it in a direction that just kind of went beyond my expectations. And most recently, this has been in what she plans to do next. So she has been working on figuring out a way and some funding to go to Costa Rica and just do this wonderful project on pesticides. And I just think that that will be a wonderful opportunity. By the way, she's from Loveland, Colorado. So I grew up in Colorado. That's a wonderful little bond. But what she's going to talk about today is really about the work she's been working on for kind of the last year and a half. And it has been a struggle of perseverance, as she will present, and that we thought this would be a lovely method that we could use. It came from an article we thought would just be plug and play, and we have had to play with a lot of getting to understand the system as a whole. And through it all, the positive attitude, the dedication has just led me to just be so impressed with Sarah and appreciate every moment of it. So with that, I will give you to Sarah.
Thank you, Deanna. It's been really nice working with Deanna. So as she mentioned, my name is Sarah Schweickart, and I'm going to be talking to you all about my project over the past year, which was about lingering lead in today's world and a method to detect lead in water using a technique called anodic stripping voltammetry. So just to start off with the basics, what is lead? Many of you may know that it's an element on the periodic table, number 82, and there's a lot of lead in our environment, but it's not really in its pure elemental form. We find it in this form called galena, which is lead sulfide, and this is very abundant. It's typically found in the outer crust, more shallow parts of the earth, and for this reason, there's been a lot of galena mines created. And I just want to go a bit into the history of lead to show just how robust the galena mining has been in our history. So here we have a graph. On the y-axis is tons of lead, and it's a log scale, and then on the x-axis is years. So back in 3000 BC, we start with the discovery of cupellation. And basically what this means is that there were little silver deposits within the galena ore. And people realized that through the process of smelting, they could separate this silver and galena, and then through the process of cupellation, they could then just isolate the silver because they wanted to use the silver in certain products that they were producing. So in the beginning, lead was more of like a byproduct, and so in the beginning we had just this discovery of cupellation. In about 1000 BC, we see the usage of coinage. And so again, this is more getting silver and then using silver but then having lead as a byproduct. But because we start to see this peak starting to grow up because of this use of coinage. Now this peak here is going to correspond with the rise and fall of the Roman Empire. This is actually very interesting, and the Romans really loved lead. And so when they first started mining it, they were again using it for silver, but they also realized, hey, lead is a great metal too because it's really malleable and soft and it's non-corrosive. So they started to use it a lot, and they used it in silverware, they used it in the roofs of their houses, they used it as sealing in pipes. Here is a Roman aqueduct. I actually read in a paper that there were 12,000 tons of lead used in the aqueduct at Lyons. And then just kind of a fun fact, this here is a lead pot, and Romans actually believed that you should use lead pots over other pots because they learned that if they heated up their wine in a lead pot, then the lead would actually seep into the wine and give it kind of like a sweetening flavor. And so they thought this was really cool. Moving forward, we kind of see a dip, but we do see a lot of lead usage in the Middle Ages, and a big example of this is the glazing used on pots. And then finally, with this big peak at the end, we have the Industrial Revolution, which is what people here may be more familiar with. This was when we used lead in many, many materials, such as pipes, leaded gasoline, and paints. And I want to point out that we talk about the Romans as, oh my gosh, it's so crazy that they use so much lead and this kind of thing. But as you can see, this is actually a lot higher, and so we are not too different from the Romans. So once we started using a lot of lead, we started to realize that it's really bad for us. Here I've put a happy person, and he's happy because he has a lot of enzymes and proteins in his body that are working properly, doing the proper functions, and he's really healthy. And within these enzymes and proteins are metals such as iron, calcium, and zinc that are shaping the enzyme in the proper way and giving it the proper function. And what lead is going to do is just swap out these metal ions and completely change the shape and the function of these enzymes and proteins and make this person sad. So because lead is a heavy metal, it doesn't really do anything but heed the enzymes and proteins from doing their proper functions. And just a few enzyme and protein functions that I found in the literature that have been heeded by the lead poisoning are vitamin D production, DNA transcription, maintenance integrity of the cell, blood pressure regulation, and sperm production. And if we go into like more of a bigger picture of what are the actual big picture health effects of lead heeding these abilities, we're going to have damage to the organs and tissues of the body. We'll see developmental delays in children and infertility. Another big thing is that lead is a neurotoxin. We've found that lead is actually replacing the calcium ions that interact in the reactions that send signals up to the brain. And so that's kind of a big deal that lead is kind of impeding our abilities to think. And then I do want to mention that lead will have a much stronger impact on children. It's been found in many studies that children absorb lead into their bodies much more than adults, and they're still developing. So this is going to be really, really dangerous for children. It's also been found that there really is no amount of lead that is not toxic. So even a tiny amount of lead is going to be dangerous, especially for children. Okay, so people started to realize that there was an issue here, and actually we knew a long time ago, but it took a long time for us to actually make any regulations and make a difference. It started in 1970. We had the Clean Air Act under President Nixon, and this was basically the act that formed the Environmental Protection Agency, and they created a lot of regulations on air pollution for a lot of different chemicals, but one being lead. So they wanted to reduce the production of lead by 90%. Here we have a graph with just the concentration of lead in the atmosphere on the y-axis and then years on the x. And I couldn't actually find one that goes back to 1970, but we can see how the lead and average levels of lead in the atmosphere have slowly decreased over time. So we've had some more regulations set. In about 1990, we had lead banned from gasoline, and then in 2008, we had tighter restrictions put on air emissions of lead. So as you can see, this is positive because we do see, at least in the atmosphere, there are a lot lower levels of lead today than there were in the past. I do want to mention, though, that this is an average, so it doesn't mean that everywhere that there's no lead in the atmosphere, but it is still a very big step. However, lead is still a big issue for many reasons. The first being that even though lead may have left the atmosphere today, when there were cities back in the past that had a lot of car pollution, these emissions could have seeped into the soils and the waters, and once they're in those bodies, they're not going to be able to leave as quickly. Next, we are having a lot of lead pollution from the erosion of paints off of houses. this is going to get to the soils and waters as well. And then this is a picture from Flint, Michigan. Many of you may know the story where they have lead pipes that are leaching lead into their water. And I just want to mention that this is not just a story in Flint, Michigan. There's actually a big problem in Milwaukee with lead, and it's in many cities, as many other cities too. So I think maybe a lot of people don't realize it's not just this one-time thing. And even going even deeper into this, lead is very much an environmental justice issue because we have these sites where lead factories were built and then shut down. These areas were renovated and houses were built upon them. And it's typically people who are marginalized groups, poorer communities, who are living on or near these factories. And it's been found that there's huge levels of lead in their soil and in their environment. You can see here that they're not actually allowed to play in the dirt because it's so bad. And there have been studies that have found that the levels of lead in blood of people and typically more marginalized groups and communities are much higher than the lead in the blood of people who are more privileged and living in cleaner communities. So I'd like to lay out 3 steps that I think we can take to start to tackle this issue. They're very broad. The first is that we need to raise awareness because I think a lot of people don't know the true extent to how lead is still a part of our lives. And if people start to know, then maybe that we can start to work together to make a difference. We need to start cleaning up our lead. And I think there are certain lead projects that have been done to clean soils and to change leaded pipes, but it hasn't been done everywhere. And so we have to focus on that as well. And then finally, we want to improve our lead detection techniques. So we want to have these techniques that are reliable, easy to use, cheap, and you can use them right on the site where the water or soil is. And so this is the concept I'm going to be going and focusing on today because that's what I did my research project on, but I do think that all of these things are really important if we're to tackle this issue. Okay, so right now there are 3 EPA-approved methods for detecting lead in our water and our soil. The first is called graphite furnace atomic absorption spectroscopy, and that's done in an instrument that looks like that. The second is inductively coupled plasma atomic emission spectroscopy, which is a pretty similar technique to the one above. And then inductively coupled plasma mass spectroscopy, which is an instrument that looks like that. So these techniques are good because they are accurate and they can detect very low levels of lead, which is what we want because we know that no level lead is actually safe. However, there are a few things about these that, for this reason, I wanted to look at using a different method. One is that, as you can see, these instruments are huge, and there's really no way that we could take these out to the field and do any on-site lead detection there. You always have to collect it and bring it back, and there could be certain contaminants that happen along the way and stuff like that. So it'd be great if we could find a method that we could eventually transfer onto the field. And then also, all 3 of these methods include kind of the same background techniques where you're basically burning your sample or turning it into atoms, and then you're detecting those atoms. And so they're all fundamentally the same. And so my goal would be to use a technique that's just fundamentally different. So that way, if there's an issue with any 3 of these techniques, it's going to be easier to see because it's a completely different method. Okay, so the method I'm using is electrochemistry. And so I want to go very basic into what electrochemistry is. So the very broad definition is it's the study of chemical processes that cause electrons to move. But if we want to get more specific into what this actually means, we have to introduce something called the redox reaction. And what this reaction is it can be split up to 2 parts: the oxidation reaction, which is the loss of electrons, and the reduction reaction, which is the gain of electrons. Now, to kind of give you a real-life example of a redox reaction, if you think about the Statue of Liberty, it's made out of copper, and when it was first built, it was actually this reddish-brown color, while now we know as this green color. And the reason for this is because there's actually a redox reaction happening where the copper is donating electrons to oxygen. And so because copper is losing its electrons, it's being oxidated, and then because the oxygen is gaining electrons, it's being reduced. So if we want to go and kind of think about more reactions that might involve copper, I'm going to introduce this reaction here, which is the reaction with zinc and copper, and we can convert this whole reaction into the two separate oxidation reduction reactions. Here the oxidation is with this solid zinc going to zinc in an aqueous solution and 2 electrons. And then the reduction would be of the copper in solution taking up 2 electrons and going to a solid copper. So if we want to visualize this, we can take a copper sulfate solution and add a zinc metal to it. And we're going to spontaneously see that these zinc ions going into solution while these copper ions are being taken up and then forming a copper metal onto the zinc. And I do want to mention that although these reactions make it look like there's little free electrons floating around in this solution, that's not really the case because it's not really how it works. It's more like the zinc is donating and then the copper is accepting. But yeah, I just wanted to point that out. And so here's a very basic picture of this reaction. And we can go even deeper into this by introducing the idea of an electrochemical cell. And so an electrochemical cell, you can actually kind of start to look at the flow of electrons. And we start off with 2 solutions, a copper sulfate solution and a zinc sulfate solution. And we can put our 2 electrodes in, a solid copper electrode and a solid zinc electrode. Now, if we attach these electrodes at the top, we might be able to expect this same reaction here to occur here, where we have the oxidation of zinc, this solid going into solution and emitting electrons. These electrons can go up and through the wire and then aid in the reduction of copper to go into this solid. And I just want to introduce here some terminology. The anode is going to be the electrode where the oxidation is occurring, while the cathode is the electrode where the reduction is occurring. That's just some terminology that's going to come in handy later in my talk. Okay, so we have this system, but we're not actually going to see these electrons flow, at least not for a very long time, because if you can imagine, as this zinc is being oxidized and emitting electrons, this solution here is going to get really, really positive because it's losing all of its negative charge. And then at the same time, the solution on the left is going to be gaining a lot of electrons and then losing a lot of positive charge. So it's going to get really negative. Because of this, we're not going to have this reaction flow for very long. We have to complete the gap. And we do this by adding a salt bridge. The salt bridge can include many things. In this case, it's potassium nitrate. And basically what this bridge does is it adds negative ions into this positive solution and neutralizes it, and then positive potassium ions into the negative solution and neutralizes it. And once we complete this gap and have this circuit, we can then have our electrons flow spontaneously. And if we put a light bulb in between here, we're actually going to see it light up because basically this is going to be electricity, the moving of electrons. And this also has applications for batteries. And so as you can see, electrochemistry has a lot of important applications. Okay, so I'm going to go even more deep into this and talk about electrochemical methods. And to talk about this, I want to introduce 2 terms. One is voltage. And the definition of this is the potential difference in charge between 2 points. So these 2 points in this system are going to be the the zinc electrode and the copper electrode. And if we put a voltmeter in between these 2 electrodes, it should read 1.1 volts every time we run this reaction. Current, on the other hand, is the rate at which electric charge flows past a point in a circuit. So this is more looking at the speed of these electrons. And in an electrochemical method, we can actually control these 2 parameters of voltage and current in order to study certain parameters in our solution. So this picture here, this whole setup is representing a very passive system where we basically put our electrodes in these solutions and then it's just going to flow spontaneously. We don't really have to do anything with it. In an electrochemical method, we're actually inducing a potential or a current on our electrodes. And so that's going to actually tell us something about our solution. And in my case, it's going to be to see how much lead is in the solution. Okay, so in an electrochemical method setup, is actually going to use 3 electrodes instead of 2, and I'll go into why that is. In my setup, I had in the middle the gold working electrode, and this is the electrode that is the electrode we're doing this experiment with. It's the one where we're inducing the current or inducing the potential. Then on the right is going to be the platinum wire counter electrode. And if you can imagine back to this picture here, these are going to be the 2 electrodes where there's going to be a different voltage. And we're going to be running this reaction and looking what's happening between these 2 electrodes. However, we do need a 3rd electrode. In this case, it's called a silver chloride reference electrode. And the reason why we need this is because if we just run this reaction here between these 2 and we're controlling the potential, we might get a graph that looks something like this, with potential on the x-axis and current on the y-axis. However, without a 3rd electrode, we're going to have no idea where our starting and ending points are on the x-axis. So even though we may get a signal, we won't know anything about it because we don't have a reference to where it starts or ends. So that's why we need this reference electrode. This is basically a known potential value that we can compare this reaction to, and then that's going to allow us to know what the numbers are on the x-axis of this graph. So that's going to connect up here, and then we have our detector that's giving us our results. Now in my solution specifically, I'm going to have water, which is any water that I want to detect for lead, a 1 molar potassium chloride solution, and you can imagine that this is basically going to act as the salt bridge in my reaction because we need these positive and negative ions to neutralize out this change in charge and actually give me a signal when I run this reaction. And then I'm adding a 500 parts per billion lead chloride solution, and I'll go a bit more into detail of that a little bit later. Okay, going even deeper into this. The electrochemical method that I'm using is called anodic stripping voltammetry, and the definition of this method is actually kind of given in the name. It's an electrochemical method to strip metal ions off of the anode by inducing a change in voltage. And so we can do this by doing 4 steps. The first is called the preconditioning step. So basically this step is, I've represented here these lead ions. This step is to try to get any lead ions or any chemical buildup that's occurred on the surface of the gold electrode. So I'm going to run a 0.8 volt potential out through this cell with stirring, and then as you can see, that's hopefully going to clean off the gold electrode from anything that's gone on there. Next is the deposition step. This is going to be holding a negative 0.5 volt potential with stirring for a certain amount of time. And this step is to reduce the lead ions onto the gold electrode. So that's going to look like this. So quiet time, we're still going to be at this negative 0.5 volt potential, but we're not going to stir. It's only about 5 seconds. And this is just to let the solution reach equilibrium. And then we do the stripping step. And so this is going to ramp the potential from negative 0.5 volts to 0.1 volts with no stirring. And this is hopefully going to strip the lead ions off. And as because they're oxidized off in the stripping step, this is why it's called anodic stripping voltammetry, because oxidation happens at the anode. So the lead ions are being oxidized off at the anode. Okay, so this is to show what kind of signal I'm actually going to get when I run this reaction. This signal is going to happen when I do this stripping step from negative 0.5 to 0.1 volts. Basically, as these lead ions are stripped off, I'm going to get a peak that looks something like this. And the depth of this peak is going to correspond with the concentration of lead that's in my solution. So my research project I started with Professor Deanna Donahue, and I found this paper called Mercury-Free Analysis of Lead in Drinking Water by Anodic Stripping Square Wave Voltammetry. And this method used the same anodic stripping voltammetry that I've discussed, but they had another method that I want to talk about, and it's called the standard addition method. And what this was they added 5 parts per billion aliquots of lead at a time, and aliquots is just another fancy word for saying small amount of lead. And as they did, every time they added this amount of lead, they performed this anodic stripping voltammetry and got a corresponding signal. So each time they increased the amount of lead, they were going to have their corresponding signal increase systematically. So this is the image they gave in their paper. As you can see, the first peak there is where they didn't add any lead, and then as they added more and more, their peaks got deeper because there was more signal corresponding with the amount of lead in solution. And they can actually use the heights of these peaks to give the initial concentration in lead in the water where there was no lead added in the beginning. So, so as you can see here, they can take the depth of the peak in this way, and they can do it for each peak, and they should get a increasing signal that will result in a linear line, and then they can extrapolate that down to the x-axis, and then that value there is going to correspond with the amount of lead that was in the solution before they added any kind of this 5 parts per billion lead. Okay, so here's me with my instrument. Here's a close-up look. So this is called a cyclic voltammeter, and it actually can run a lot of different electrochemical methods, and one of them being anodic stripping voltammetry. If you can see here, it says BASI at the top. I think that's how you pronounce it. That's just the manufacturer of it. And if you want to look closer at what the electrodes actually look like, on the left here is this silver chloride reference electrode. On the right is this platinum auxiliary electrode, and then in the middle we have our gold electrode. And I just want to point out that this little tiny circle there is the actual gold surface that this reaction is occurring on. So these lead ions are actually going to be formed onto this little tiny surface. So once I set up my cell, I can then go onto the computer and open the software and pick the electrochemical method that I want to run. So here is square wave stripping voltammetry, and I can put in my parameters. The first step I ran, the first procedure I ran, was to just follow exactly what the paper said. So my preconditioning step was 800 millivolts for 5 seconds. My deposition was negative 600 millivolts for 180 seconds. Quiet time for 5 seconds. And then stripping was negative 600 to 100 millivolts. Okay, so here is what the paper gave, and here's what I got after my first test. So this was kind of exciting because it looks kind of similar, right? We have peaks getting deeper as I led, and it seems pretty systematic as I added lead. But when we took a closer look at this, we realized there's certain things going wrong that's going to affect our data. For example, you can see that my peaks are shifting to the left a lot, whereas the peaks here are just going straight down. And so that's a problem. We should probably figure out why that's happening. Also, if you just look at the first and last peaks of this, the first peak looks pretty good. It looks almost the same as this one. But the last peak, if you actually look at the depth, this one is very, very large, whereas this one almost looks smaller than the first one. So I'm not getting this peak coming back up to be large enough to actually be able to get the data that I want. Okay, so once we saw this, we had a discussion about some things we might be able to change to fix this. So the major parameters we talked about was, let's make sure that the instrument is actually working. Are we cleaning off the electrode well enough? Are the electrodes actually working? Is the deposition potential at the right potential to reduce lead? And is the deposition time long enough or too long to reduce these lead ions onto the surface? So to start off, I wanted to verify that the instrument was actually working. So I followed this BASI tutorial. Basically, the manufacturing company just gives this layout of, okay, make this solution, put it in the cell, and run all these tests to see if it's working. And so these tests included cyclic voltammetry, chronocoulometry, and chronoamperometry. It sounds very complicated, but basically I just put it in the software and then tried to see if I could get the same images that they posted, and I did see that. So from that, I thought, okay, I think my instrument's working, so let's move on to the next step. Okay, so I had a suspicion, and I had read in a lot of papers that cleaning is really important in anodic stripping voltammetry. And the reason for this is because if it's not cleaning it off well enough, then plated metal and other gunk is going to just kind of form on the surface of the electrode like that. And if this occurs, then when you actually do this, the step where you're trying to reduce lead ions onto the surface, there just isn't really going to be as much going on. And so when you then strip them off, you're not going to get the same signal as if they were all forming and all coming off efficiently. And so I thought this might need me to change and adjust this preconditioning step. So I want to just quickly talk about this idea of physical polishing versus electrochemical polishing. With the gold electrode, there is a physical polishing procedure where basically you have this pad and some sort of alumina or diamond polish, and you wet down the pad, you add your polishing, and then you move the electrode in a figure 8 motion like this for several minutes, and once you do that, your electrode should be clean and you can set it up in your cell. Then we have electrochemical polishing, which is what I talked about earlier, where you have this 0.8 volt potential with stirring, and then this is hopefully going to clean off the surface of your electrode. And so basically my goal was that physical polishing is good to use at the very beginning of your experiment because you're just starting off new, you polish it up and then put it in the cell. But then in between adding lead, it would be a big pain to have to remove the electrode every time, polish it, and then put it back in. And so in between experiments, I wanted to find an electrochemical step that was going to work to properly polish the gold electrode. So my first test was the cleaning of this electrode, and I was changing my preconditioning step method. Now, I didn't go into detail of what actual methods I used. Basically, I was changing around the potential I was using and how long I was using it for, and it was based off of certain papers that I read and stuff like that. And I just want to, and then finally this repolishing step was when I actually removed the electrode and polished it and put it back. So this repolishing step is going to correspond with this peak here. And basically what we can see is that that is the only step that's after we're doing it, it's kind of giving us back to this first really nice deep peak, whereas all these other ones, our peaks are getting really almost non-existent there. And so I thought this to mean that physical polishing is probably the most effective cleaning method. But I still wanted to see if I could find an electrochemical method. So I tried messing around with stirring during the method to see how it would change. And so again, these methods, I won't go into detail, but I was changing if I was stirring or not during the method. And I want you to pay attention to cleaning method number 2 because I repeated it 3 times. And each time, it's kind of staying consistent with the peak before it. So it seemed like it was being more consistent than the others. And this step was actually, I had constant 800 millivolts for 2 minutes with stirring. And so I found this to show that stirring will result in larger and more consistent peaks. And then I also decided to use this method in future trials because it seemed to be pretty accurate at giving us consistent peaks. Next, I wanted to see if I changed out my reference electrodes, if this would make a difference in the signal. So I just basically, with the same solution, changed the kinds of electrodes I was using. And as you can see, these peaks are changing somewhat here, but it's fairly consistent. So I thought this is probably not a reference electrode problem. I do want to point out that this was the cleaning electrode test from earlier. And if you notice, these peaks are much more consistent and much deeper, like a better signal than these peaks. And so I found this to be due to 2 reasons. Well, maybe 2 reasons. Basically, throughout these trials, I was tweaking little tiny things along the way. For example, I talked to Graham about this and he suggested to do some things. So I remade my potassium chloride solution and I changed the way I was physically polishing my gold electrode with a different kind of polish. And I think that doing these little things actually greatly enhanced the signal that I was seeing and how consistent it was. So I just wanted to point that out. Okay, next I wanted to see if changing the gold electrodes would do anything. So basically I took 2 different electrodes and I ran the same test where I added concentrations of lead and looked, and then had the peak, looked at the corresponding peak height. And as I showed earlier, it should be like a positive increasing line here, but instead it's kind of like both of them are staying flat, but both of them are about the same. And so I thought this isn't really a problem within the working electrode. Okay, next I wanted to see deposition time. So First, what I did was I tested for the same solution if I just did 30 seconds of deposition time up to 150. And pretty clearly here, it seems like these peaks are getting smaller, and we were surprised that the 30-second peak just seemed to have a really nice signal. And so we thought, okay, a larger deposition time gives smaller peaks. And then we thought, well, maybe this is because when we're having a really long deposition time, this is just putting too much gunk onto the electrode and it's not completely stripping off. And so we just tried doing 1 second to 60 seconds. And as you can see, these peaks are probably the best we've seen yet. They're just really consistent. And so we thought, okay, maybe that means we just have to do a shorter deposition time. Next, I wanted to see how changing the deposition potential would change our peaks heights. So I did a -200 to -700 potential on just the same solution. And what I've found pretty clearly is that a lower potential is going to give a larger peak. But I do want to point out that with this -200 and -300, the peak's actually getting cut off here at the beginning, and with further trials, with -300, I was getting it looking something like this -200, and so if it's cut off, I couldn't actually tell what the peak height actually was. And so for that reason, I decided to go a little bit lower, so like a -400, -500 potential. Okay, so if I put all of these new parameters together and test it, preconditioning step for 800 millivolts was stirring for 2 minutes, a deposition of -500 millivolts for 3 seconds, quiet time for 5 seconds, and then stripping -500 millivolts to 100 millivolts. Here's what I got. And if you think back to this picture here, well, it is better. There's less drifting to the left. There's still a little bit of drifting, but not as much. And the peaks here are looking pretty consistent to those there. But we're not actually seeing our peaks getting any deeper. And so it seems like we're not actually seeing any lead signal. So even though we've improved, we're still not quite there yet. And I just want to mention that one reason this could be is because the anodic stripping the anodic stripping voltammetry technique is typically used with a mercury drop electrode rather than a gold electrode. And so this could have been, and also this was, me like tackling on this technique that had never been done at Lawrence before. And so it's not too surprising that I couldn't get it completely to work with my time here, but I guess I'm happy with how far I got. So some of the results, we found that the ideal deposition range is -0.4 to -0.6 volts. A shorter deposition time gives more consistent peaks, but we're not actually seeing a signal. Cleaning is really important, and don't forget the small details because those had a big play on how much signal I was seeing. A summary, lead is still an issue and we need to do something about it. Anodic stripping voltammetry is a potential novel method that we could use for the detection of lead in water. Analytical research is hard but important. And here I have a picture of me very loving with, and also wanting to strangle my instrument. I had mixed feelings about it. And next steps, I think if I was to work farther on this, I think I might need to take a step back and look at the actual solutions that I'm using. So maybe it's something with the lead chloride solution or something like that that's going on. So that might be what I do next. So acknowledgements. I want to thank Deanna Donahue for being my advisor through all of this and helping me push through. Graham gave me some really helpful tips, electrochemistry tips when I went to him. Dave Hall and my Chem 680 classmates gave me some good tips on my slideshow. Daniel Martin and his stockroom staff were very helpful throughout all of this. I want to thank Anthony Alvarez because I practiced a lot with him and he put up with that. And then the Chandler Senior Experience Funds are just what helped to fund some of the parts of the project that I did. So yeah, any questions?
When you were introducing this idea of like all the mass spectrometry techniques that are used now to detect lead, obviously those aren't feasible, so bringing to the field. What do you think something like cyclic voltammetry or like your anodic stripping method, what do you think that would look like in the field?
Yeah, that's a good question. So clearly here we're just still in the very first steps, but I think because these electrodes are kind of in a smaller system and I think there are ways that you can just have maybe 3 electrodes in like a smaller setup where it's possible in the future we could develop something that could be brought out in a smaller portable instrument rather than these mass spectroscopy machines that are just huge, and there's probably no point in the future in which we can make those smaller and bring them out to the field.
Sorry. So I was also wondering, just like in terms of cost, I assume cyclic voltammetry is much cheaper than mass spec, but I was just wondering if you have anything.
Yeah, well, in terms of cost of the actual instruments, I'm not sure, but I know that with this paper, the actual setup wasn't too difficult. I mean, we had to order some new electrodes, and those weren't super expensive, and the lead chloride solution and the potassium chloride were pretty simple. So I think in terms of that, it really wasn't too much of a cost.
So you mentioned that wine became more delicious with in a lead top. And so that would suggest a pH sensitivity. And indeed, they discovered that in Flint, Michigan by running long pH of water through and all the lead came out. So did you look at the pH of your potassium chloride solution, and could that be well, we can make a joke, a potential problem? Is the uneven pH, or did you try different pHs or a buffering system?
Yeah, so I actually didn't look at that, but that's a good point. One thing Graham mentioned to me that I didn't have time to do was that I could add the potassium chloride to my lead solution as I'm making the lead solution, and so that way that's consistent throughout the entire experiment, but I just didn't have time to do that. Yeah.
What was the pH of your water because your solution is 3.11?
Oh, does that mean it's just 7? Okay. Yeah, I just, in the beginning, I used just like NanoPure or DI water, and then as I progressed, I switched to just using HPLC water. So that was to hopefully keep anything out and keeping the pH constant.